This video covers the last regression technique we're going to discuss in this class, and that's logistic regression. So we've covered linear regression beforehand, where you want to test if two continuous variables are related to each other. But what if the dependent variable has a binary outcome? So binary or binomial means that there's only two outcomes, yes or no. So for example, does size affect survival of organisms during an extinction event? So this is binary because there are only two possible outcomes. They either go extinct or they don't go extinct. So why can't we just fit a linear regression line like I've done here? Well, let's think back to the assumptions that linear regression makes. So first of all, the relationship of the actual data is not linear. I mean, I put a linear line through it, but that's not the relationship that you see from the points. More importantly, the variance of the y values is not constant for all x. It's going to be sort of greater variance in the middle where you have a lot of data at both 0 and 1, but as you get close to large sizes, the variance is quite small because there's very little data at the 0 line. And also, the residuals in the y direction around this red line are certainly not normally distributed either. They're bimodal, in fact. Conceptually, a linear regression fit could also imply that we would get probabilities greater than 100% or less than 0%, and that doesn't make a lot of sense. So that's where logistic regression comes in. It's designed when you have at least one continuous independent variable and a categorical dependent variable. And so the dependent variable must have only two levels in that category. So it's binomial or binary. Like other regression methods, the purpose of logistic regression is to test whether the independent variable, the continuous one, has a causal effect on the outcome of the dependent variable. And the null hypothesis is that there's no effect, so that changes in the independent variable do not change the probability of the outcome happening. Size does not affect the probability of extinction. So a couple slides ago I mentioned that one of the problems with applying linear regression, aside from the fact that this sort of data violates almost all the assumptions, is that it can imply probabilities greater than 100% or less than 0%, which obviously can't be correct. So we need to find a way to make sure that the probability is always between 0 and 1. And so one way is to use a function to transform the numbers from the range between minus infinity and positive infinity to the new range of between 0 and 1. So a function is just an equation that maps numbers from one range, called a domain, to a different domain. So we're going to map numbers from the domain between minus infinity and positive infinity to the new domain between 0 and 1. And logistic regression uses a function called the Logit function, which is this equation given here. So here's how the method works. Remember, the linear regression equation describes the dependent variable y in terms of an intercept, beta 0, a slope, beta 1 times the x value, and then each point is going to have some residual because not all points fall exactly on the line. So if we do that, we get something like the red line in the top graph here, which is obviously not a good description of the relationship. But after applying this Logit function, we then get the equation at the bottom where pi I is the probability now that the outcome occurs. So pi I is the probability that y equals 1. And so the regression line now, after transforming it with the Logit function to get 1 over 1 minus e to the minus equation there, is now bound between 0 and 1, which is what we want, this curved regression line here. So this equation here is the equation for logistic regression with the pi I, but it's more common or more typical to see the equation in this rearranged form, expressed as the log of pi sub I divided by 1 minus pi sub I. And so that is called the log odds. This log of pi I over 1 minus pi I is the log odds. We'll discuss odds in a bit more detail in the next slide, but briefly, the odds are the probability of an event occurring, pi I, divided by the probability of the event not occurring, which is 1 minus pi I. And so these are log odds because we're taking the logarithm of that odds. So in our equation here, and we have at the top, a positive coefficient beta 1 means that the odds of the outcome increase. And so the probability pi I also increases. So as the independent variable x increases, the odds of the outcome also increase. So I'll just very briefly mention how the significance testing works, but it's not that important particularly. It's analogous to linear regression. So linear regression assesses the significance of our test statistic against the t distribution, where logistic regression uses a normal distribution. So we evaluate the probability of finding a coefficient which is converted to this z-value. So we want to know what's the probability of getting the coefficient at least as extreme if the null hypothesis is true. So this is fairly standard p-value calculation. Okay, well, back to our coefficient. So this logistic regression coefficient beta 1 is something called the log odds ratio. So this is different than the log odds because an odds ratio is comparing the odds between two different groups. So for example, we can say in case 1, the odds are the probability of success divided by 1 minus the probability of success. That's the definition of odds. And we can have the same in case 2, same way that odds are calculated. And so the odds ratio is just the ratio of the odds for case 1 divided by the odds for case 2. And so in logistic regression, because our coefficient beta 1 is the log of the odds ratio, the actual odds ratio itself is just e to the power of that beta 1. So basically what the odds ratio is telling us is the odds of the outcome when the independent variable was x plus 1 divided by the odds of the outcome when the independent variable is just x. So in other words, this is telling us for every 1 unit increase in the independent variable x, the odds of the outcome happening are multiplied by e to the beta 1. So basically, in the example that I gave at the very beginning about how does size affect extinction risk, we could say that every 1 centimeter increase in body size would increase the odds of extinction by e to the beta 1. So when reporting the results of logistic regression, the log odds ratio, which is a measure of the size of the effect, and the p-value are the most important points. You might want a scatter plot showing the data like I've illustrated in this video here, although you don't often see that. It isn't commonly given in papers that do this. If you're comparing the effect of different independent variables, you want to know which of these is the most important contributor to extinction or whatever. Or if you want to look at the effect of a particular independent variable across different groups, like different time periods or different environments or whatever, you could plot the log odds ratios and their confidence intervals to visualize whether each one overlaps with 0 or not. There's sort of ways that you can graphically illustrate this, but really the fundamental things are the log odds ratio and the p-value. So the R command for logistic regression can be found within this function called GLM, which performs something called generalized linear models. Note that this is different from the general linear model, which I mentioned before in the ANCOVA video. So the syntax is similar to linear regression. You use this formula equation with a dependent variable as a function of the independent variable, and you can specify the data frame that they occur in with data equals. But the one difference here is you have to indicate that you want the family equals binomial. Specify that the binomial link function is what you want, because GLM can do a bunch of different regression type models. So remember that the dependent variable should be a factor with 2 categories. It doesn't have to strictly be a factor variable in R as long as there's only 2 categories, because R can sort of force that into a factor as it's doing this. And the independent variable should be a continuous numeric vector if you only have 1. You can do multiple logistic regression with multiple independent variables, but we're not going to really discuss that. So the output will look something like this. There's quite a lot of information in it, but there are some similarities with linear regression that you've seen before. So it gives the distribution of the residuals, which are called the deviance residuals here. And it also gives the coefficients. This is the important part, the log odds ratio, which is in the estimate column, and its p-value. You also have the standard error of the log odds ratio, which is useful if you want to calculate a confidence interval on it, and the z-value that it converts the statistic to. The bottom part, which has the null and the residual deviance and this AIC thing and the Fisher scoring iterations, are just details about how well the model fits and how the model fitting procedure occurred. So we don't really need to pay attention to those because they're only really informative when you're comparing multiple models to each other. And hopefully you won't get this warning message at the bottom that I got. It means that there's either perfect or something called quasi-perfect separation between the outcomes. What this means is basically like all of the yes outcomes are at one end of the independent variable and all the no outcomes are at the other end, more or less. In this case, in the data that I use, there are very few that actually survive, and they're all very small. So it still runs a regression. It's a warning and not an error. But the warning sort of tells you that what often happens is that the coefficients themselves, the estimates might be inflated, might be larger than they really should be. So there are ways to deal with this, but I'm not going to cover them, but just sort of take note that if you get this warning message, you might want to sort of reevaluate the model that you're running and look into it in more detail. But really, for our purposes, the key thing is to look at these coefficients, particularly which tells you how the independent variable, length in this case, affects extinction risk. The log odds ratio, 0.23677 here, and the p-value are kind of the key things that we're going to be looking for in this class.